Good afternoon. This is MCS Geometry, Lesson 72, page 477, and it is called Tangents and Circles, Part 2. We are going to go through the warm-up. A warm-up is a line that is in the same plane as a circle and intersects the circle in exactly one point is called a tangent. Yes. It's hard to write when you can't see it. Thank you. Number 2, R and S, as shown in this diagram, and RT are tangents to circle A. We are to find each length. So what we remember is that RS is congruent because it is two tangent lines which intersect at an external point, that these segments are congruent. So RS is congruent to RT. Find each length. Since they are congruent, we will set the two numerical algebraic values. 4x plus 1 equals 3x plus 6. We will solve for x so we can get a numerical answer. We subtracted 3x from both sides. We subtracted minus 1 from both sides, and we got x equals 5. That's not our answer. Next, we plug it into one side. So we plugged it into 4 times 5 plus 1 equals 21. And we plugged it into 3 times 5 plus 6 equals 21. Indeed, they are the same. Number 3 of your warm-up says draw a circle with a tangent line, a chord, and a secant, and label each line or segment. And that being your hint that you need to make the difference. Well, your tangent line is a line that intersects at one point, and I labeled it T. The second one was to have a chord. A chord is a segment which intersects in two spots, and I will call it C and H, first two letters of chord. And the secant also intersects in two spots, but it is a line, and I labeled it S. Over here, the chord is CH, segment. The secant, I labeled it as line S, and the tangent I labeled as tangent T. Make sure these basic circle identities are drawn on your smart sheet to your satisfaction so that you can recall the specific differences. Lesson 72 is called Common Tangents. Common tangents. I drew two sets on one page. Please look at the solid lines. Two different circles, both tangents. This one line is tangent to both circles. This one line is tangent to both circles. If you imagine them extending off the page, they will intersect at an external point C. These lines are external to the position of the two circles. Our next relationship is these dashed lines. This is a dashed line which is tangent to both circle B and circle A. And this is also a tangent line to both circle B and circle A. And they intersect at a point external to the circles, but internally to the relationship between the two circles. So it is still an external point, which still gives us the same rules as before. Two tangent lines which drawn from an external point to the circle are congruent. So we will be able to use this. I will review this over here. Remember, Theorem 58.3. If two tangents are drawn to a circle from the same exterior point, then the tangent segments, D to the circle, D to the circle, are congruent. I labeled them external as the solid line for common tangents and the dashed line for the internal. And I named them N and X and X. That is the new concept, but we are using our previous learned theorems to solve it because we still know now that these two are in relationship to each other and these two are in relationship to each other. And this length is in relationship to this length, And this length will have a ratio similar to this length. We still have 2 points. So going over to the example 1, I've drawn example 1, which is on page 477. Circle A and circle B are congruent circles, and MR, line MR and line PM are internal common tangents to circles A and B. Find the length of MQ. Well, we're going to write down some of our givens. We know from our relationship of theorem 58 that QN is congruent to QR and MQ is congruent to PQ. And I wrote those right here, definition of congruent segments. And we can see how it's labeled that QR is given a numerical value of 12. QN is given an algebraic value of X. MQ is given an algebraic equivalent of 2x minus 10. And that is what we're looking for is MQ. So given that we know what, so we can now set, according to the top, that X is congruent to 12. And if X is congruent to 12, X is now 12. Let's plug in 12 right here, and we will get 2 times 12 minus 10 equals MQ. So what is 2 times 12? 24 minus 12 is 12. You may pause at this point because I'm going to go over the practice problems. If you are coming back, practice problem A is on page 479. I will bring it in on the book over here. And it says that in the diagram, RT and QU are both tangent lines to the circles. Find the lengths of RS, ST, and SU. They didn't ask for QS because it's already been given. So here's what they asked. Find RS, ST, and SU segments, and they've given us segment QS equals 8. Well, I've now written down the other relationships shown on the diagram, that x plus 3 is an algebraic equivalent to RS, 4x minus 7 is an algebraic equivalent to segment ST, x plus 8 is an algebraic equivalent to segment SU, and 8 is the numerical equivalent to segment QS. Well, what do we know? We know from this that RS is congruent to QS and that segment SU is congruent to segment ST. So we're going to substitute in x plus 3 equals 8 and also x plus 8 equals 4x minus 7. We're going to solve for x and find our lengths. At this point, you can find that x equals 5. And so x plus 5 is 13, which equals 20 minus 7, which is 13. So our lengths of x plus 8 are congruent to 13, and our ST is 13, and our segment RS is indeed 8, which is what we would expect from the original. Very good. Practice B. Practice B, you can pause and do it yourself. Come back. These are the two relationships of finding of tangents and of also finding a triangle. In this case, we have two tangent circles, tangent at this point right here, And they are, the problem states that P and Q are congruent tangent circles with radii of 6 inches each. So radius 1 and radius 2 is showing this length. However, we are given that radius 1 is congruent to radius 2, and we know that the length of PQ then can be labeled as 2 times R1, and that, again, R1 is 6 inches. Well, what is the area of our triangle? Well, it equals 1/2 base times the height, which equals 1/2 times what I'm calling the base here, R1, and the height, RQ. Well, RQ we don't have yet, and it is one of the sides of our triangle. Using Pythagorean theorem, R1 squared plus RQ squared equals the sum of radius 1 plus radius 2 quantity squared. That gives us 6 inches squared plus RQ squared equals 12 inches squared, which equals 36. RQ squared plus equals 144. That ends up giving us RQ squared equals 108 inches squared. To take the square root, it equals the square root of 108. Over here I did a prime factor and got 2, 2, 3, 3, and 3. I put them inside the square root. The two 2's come out as 2, the 2 3's come out as 3, 2 times 3 is 6. And I wrote 12 by mistake. 6 times the square root of 3 inches is the length of RQ. So let's go back up to our original area question. 1/2 6 inches times 6 times the square root of 3 inches, which equals 18 times the square root of 3 inches squared, which equals the area of the triangle of PQR. You may pause again. But thank you very much. We're going to leave C. Says that 19 feet was one part of the pulley. I will zoom in. And the second half of the pulley is 5x minus 6 feet. Hence, 19 equals 5x minus 6. You will solve. Doing so, you will be able to solve for x and find out that, well, without any guessing, they want you to find x because they're assuming that you know that DE is 19 feet. Thank you very much. Have a great day.